65 million years ago, a 1,000 billion-ton asteroid smashes into the Earth, wiping out the dinosaurs. Massive impact events are likely to happen once every 75 million years. Today, scientists scan the skies for these giant killers. But an asteroid just 150 feet across could devastate a city the size of New York. Asteroids this size could hit any time. And right now, there is nothing we can do to stop them. It's a nightmare scenario. 1,000 billion tons of rock on a collision course with Earth, hurtling towards it at over 50,000 miles per hour. It hits with the force of 300 million nuclear weapons. Enough energy to wipe out every human being on the planet. This is no nightmare. It's real. 65 million years ago, a rock this size smashes into the Earth. And wipes dinosaurs from the face of the planet. It could be 10 million years before the next impact this big. But smaller asteroid impacts can also be devastating, and they happen far more often. Around 50,000 years ago, an asteroid slams into the Arizona desert, hurling 175 million tons of rock into the air. Meteor crater is nearly a mile wide and 570 feet deep. Amazingly, the Canyon Diablo asteroid that created it was only 130 feet in diameter, about the size of a small jet plane. There are more small asteroids like this in space than large ones, and they can hit the Earth as often as every few hundred years. One scientist at Northern Arizona University thinks Meteor Crater has a message. Professor Ted Bunch.
Events like this, smaller events, they could happen anytime.
And they're capable of massive destruction. The extreme heat of this blast tore through the desert sandstone.
This is coconino sandstone, and it's in pretty good shape. And there's a piece here. This is also coconino sandstone that is severely shocked. Probably temperatures exceeding maybe 3,000 degrees Fahrenheit. Huge amount of pressures, and you can see the difference. This used to be this.
Imagine the same thing happening today. What would a 130-foot wide object like this do to New York City?
If this meteorite had hit Manhattan yesterday, about 80% of the people would have had serious injury or died. All the boroughs of New York would have been affected, either by the heat, the shock wave, the seismic activity, crumbling of buildings, and collapse.
Everything within a 5-mile radius would be obliterated. Asteroids have crashed into our planet ever since its formation. The key to their destructive powers lies in their mass and the speed of impact. As an asteroid hurtles towards Earth, it builds up huge amounts of kinetic energy, much like this speeding car. The faster the car goes, the greater the kinetic energy, even though the car's mass stays the same. When the speeding car hits a brick wall, it doesn't inertly stop. All the kinetic energy is converted into an explosive force. The crash generates heat, metal bends, plastic and glass shatter. An asteroid behaves exactly the same way when it impacts the Earth. Only because it's traveling at 50,000 miles per hour, the explosion is far greater. Here in Arizona, evidence of the impact stretches 6 miles from the crater's edge. Pulverized rock particles called impactites shot across the landscape at deadly speeds.
We have impactites, all these little dark guys. Those are melt rocks. There's literally tens of thousands of them right in this particular area. These were ejected as far as 3 to 5 miles under very high velocities, 2 or 3 times the speed of a rifle bullet. But if you were an animal in this area and you had thousands of these particles coming at you, you'd be toast.
Impactites are a major clue to an asteroid strike and can reveal previously unknown impacts. Fossil hunters in Alaska uncover fragments of tusk from woolly mammoths. They are peppered with buckshot-like particles and date back 34,000 years to a time when the number of large mammals in the region inexplicably dropped. Have fossil hunters uncovered evidence of an undocumented asteroid impact? Dr. Richard Firestone searches for evidence.
We analyzed several of the particles from various tusks, and they had the unique signatures of meteorites. They were rich in iron and nickel, which is a critical component of most meteorites.
This is strong evidence that these woolly mammoths died from an asteroid impact. The force of blast was devastating.
We did an experiment with a shotgun to see what would happen if you shot a mammoth tusk, and they simply bounce off the outside. Nowhere near enough energy for that.
A shotgun fires at 600 miles an hour. Asteroid fragments travel over 30,000 times faster.
In order for the impact particles to penetrate the tusks as they did, they'd have to have been moving at tens of miles per second.
Firestone's mammoth died in an asteroid impact 34,000 years ago. The impactites embedded in the mammoth tusks prove that previously unknown asteroids have struck the Earth. And new evidence reveals that they didn't just kill mammoths. Humans died too. 13,000 years ago, North America is locked in an ice age. Large mammals like giant sloths and woolly mammoths roam the land. The nomadic Clovis people live alongside them. Then the fossil record stops. Many species of mega mammal abruptly disappear. What causes this sudden, mysterious disappearance? The Clovis culture also vanishes from the archaeological record. Is it starvation? Disease? No one knows for sure. Now a cave in northern Ohio may hold the answer. 30 feet underground, an archaeologist from the University of Cincinnati discovers evidence of an ancient catastrophe. Ken Tankersley and his team dig up a layer of burnt material in the soil. It dates to when the Clovis and the mammoths vanished. To archaeologists, this distinctive carbon-rich layer, called the black mat, indicates intense burning, a sure sign of a destructive event.
Beneath this layer, we have evidence of large mega mammals. Above it, there's none whatsoever. This mat was deposited in a very quick and sudden event. Beneath it, you have evidence of Clovis people. Above it, you have absolutely none. The real mystery is what happened at this very time.
What catastrophe caused this black mat? Tankersley searches inside the black mat and uncovers the bone of a wild pig, known as a peccary. It tells a disturbing story.
This particular bone has not seen air in 13,000 years.
the bone shows signs of extreme burning.
We know this burning is not the result of cooking. These animals were larger than I am, and to take a human body and a natural fire, you have to burn the body for days. This type of burning clearly came from a very intense, very fast burning, a single event fire, if you will.
Did an asteroid cause this deadly blast of heat? If it did, there is a vital piece of the puzzle missing. There's no evidence of a crater. This leads to a disturbing possibility. Could an asteroid be big enough to destroy an entire culture, yet so small it leaves no trace? Around 50,000 years ago, a small 130-foot wide asteroid smashes into the desert of Arizona and creates Meteor Crater. An impact this size could wipe out a major city. But this isn't the last time Earth was hit by a small but deadly asteroid. We're realizing that Earth is far more vulnerable than we once imagined. And some devastating impacts have left almost no trace. Archaeologist Ken Tankersley has found a black mat, evidence of an extreme heat event in a layer of rock dating back 13,000 years. The same time that the Clovis culture, one of the earliest in North America, abruptly and mysteriously vanished. Is an asteroid responsible? New research at sites across the United States also uncovers the black mat layer of burnt material, all dating back to the same time. The chemical analysis is compelling, but Tankersley wants to be even more certain. He returns to the Sheridan Caves in Ohio to take further samples. At the University of Cincinnati, an electron microscope takes a close-up view. Tankersley magnifies the tiny sample 10,000 times. He spots compelling evidence of a devastating asteroid impact. Detonation diamonds.
What's kind of tantalizing here is the possibility that these are associated with a cosmic event, if you will. Detonation diamonds are the result of a strong impact from either a large meteorite, an asteroid, or a slice of comet.
Major asteroid impacts have shaped history more dramatically than ever imagined. It seems increasingly likely that an asteroid is the reason for the Clovis culture's disappearance 13,000 years ago.
In geological time, 13,000 years ago is yesterday. The implications for us living on the planet today, we always think it's not going to happen to us. The reality is when it's going to happen next.
No one has ever found a crater from this event. So the question is, how big was the asteroid that caused this catastrophe? Asteroids are mostly composed of rock and metal, debris left over from the formation of the solar system 4.5 billion years ago. Thousands of these objects orbit near the Earth, some as big as mountains, others smaller than a speck of dust. The size of the asteroid that may have ended the Clovis culture is a mystery. One scientist thinks he can find the answer. Professor Peter Schultz of Brown University starts with one vital piece of information. The Clovis culture ended during an ice age. 13,000 years ago, North America is partially covered in a layer of ice up to a mile thick, the Laurentide Glacier. So the question is, what happens when an asteroid slams into ice rather than land? Schultz suspects the asteroid would leave a crater in the ice, a crater that might eventually melt, hiding all evidence of the impact.
The fact is, ice was there, and there's no reason why an impact couldn't hit there as well as any other place.
Schultz tests his theory in the vertical gun range at NASA Ames Research Center outside San Francisco. The vertical gun is unique. It can fire projectiles at 13,000 miles per hour, equivalent to the speed of a real asteroid. Schultz must find the exact ratio of asteroid size to ice thickness to cause a devastating explosion, but leave no crater. He uses a tiny glass bead in place of an asteroid and a half-inch sheet of ice for a mile-thick glacier. The experiment will tell Schultz how much damage a half-mile wide asteroid would cause.
We got about 3/4 of an inch of sand in there. We're going to be firing a projectile about a 1/4 inch across, but the question is whether or not it's going to penetrate all the way through.
An asteroid colliding with Earth smashes into the atmosphere. Friction superheats it as it plummets through the air. Schultz simulates Earth's atmosphere by filling the chamber with argon gas. The gun will fire the projectile at almost 4 miles per second, the equivalent speed of most asteroids.
Every time you do an experiment, you learn something brand new. I love surprises, and invariably we have a surprise.
Could an asteroid be small enough to leave no crater, but big enough to devastate large parts of North America? It's a pressing question. The solar system is full of smaller asteroids. During the last ice age 13,000 years ago, an asteroid may have incinerated parts of North America, but left no crater. Scientists are trying to find out how an asteroid could be big enough to wipe out an entire culture and yet leave no imprint. Peter Schultz uses the vertical gun range to test what happens when a half-mile wide asteroid hits a mile-thick sheet of ice.
Oh! Pow! Oh my gosh! That's gotta hurt. Did you see that? Look at that stuff. Man, that hurt.
A glass bead enters the chamber at 13,000 miles per hour. When it hits the gas simulating our atmosphere, it burns and then explodes. A fireball smashes across the ice.
This is when you say, oh crap. It's coming for you. You can't even hear it because it's going faster than the speed of sound.
The experiment shows that a half-mile wide asteroid hitting a mile-thick ice sheet would have catastrophic consequences.
Oh wow, there's no crater. You don't even know that it happened. Let me go ahead and take some pieces out, okay? Here's where one big mass hit. You can see the little pit in there. If the ice hadn't been here, we would have formed a crater about that big. The ice acted like a flak jacket. You know, once this goes away, once the water goes away, you can't tell that anything was here. That's remarkable.
The after effects of the impact would have been felt as far away as Europe. But the asteroid itself leaves no crater.
All you need is an object about a half-mile impacting into that. It might have formed a crater 20 miles across, but when the ice disappeared, melted, went away, you might completely remove the evidence. It's kind of like a perfect cosmic crime.
The asteroid that may have ended the Clovis culture could have been just half a mile in diameter. An estimated 1,000 asteroids of around this size hover near to Earth at this very moment. Scientists decide to look at other more recent impacts in order to reevaluate their size. One of the most famous and powerful recent asteroid impacts is known as the Tunguska event. June 30th, 1908, an asteroid explodes over Tunguska, Siberia with the force of 1,000 atom bombs. Tunguska is so remote that it takes 19 years for scientists to mount an expedition to examine it. The team brings survey equipment to record the devastation. The blast tore 60 million trees out of the ground. 800 square miles of Siberia, an area 1.5 times the size of Oklahoma City, are flattened and scorched. There is no crater. The asteroid exploded before it hit the ground. The size of the asteroid remains a mystery for almost 20 years. Then in the 1950s and 60s, impact specialists attempt to simulate the strike using data from nuclear tests. Some scientists estimate the Tunguska asteroid was up to 600 feet across. That estimate has been reduced to around 200 feet. In 2007, Dr. Mark Boslow reanalyzes the data using a supercomputer. He thinks the asteroid is much smaller.
Most of us had been thinking that it was an asteroid, came streaking in, it got down to about 5 miles above the surface and exploded with an energy of between 10 and 20 megatons. So we knew roughly what the wind speeds and what the thermal effects would be on the ground for an explosion at that height and that magnitude. And what was observed at Tunguska was consistent with that.
But this theory assumes a nuclear weapon and an asteroid impact in the same way. A nuclear weapon explodes from a single static point. But an asteroid is different. It's moving fast. So when it explodes, the energy it releases keeps moving, causing even more destruction.
When it explodes, it vaporizes, it begins to expand. It's very much like a nuclear explosion, except it's got a lot of mass and it just keeps on moving.
So the explosion over Tunguska spread out across the landscape.
We realized that even though it explodes at this high altitude, that explosion continues downward. All that hot rock, all that vaporized asteroid material continues downward, and finally it slows down and finally stops a few miles above the surface. The blue color here represents the shock wave, that blast wave that carries mechanical energy down. So that's very high wind speeds, hurricane force wind speeds. So when that hits the ground and sweeps across the ground, that's blowing trees down.
The old model assumed a stationary explosion. That meant a 200-foot asteroid. The model was probably wrong. A moving object could be small and still cause that much devastation.
The Tunguska event could have been caused by an asteroid as small as 100 feet in diameter.
Boslow's findings sent shockwaves through the scientific community.
There are many more smaller asteroids in Earth-crossing orbits than there are larger asteroids. Therefore, if Tunguska was from a smaller asteroid, a Tunguska-like event is more frequent than we had previously thought.
Scientists once thought an asteroid around 600 foot wide caused the obliteration of Tunguska. A rock that big hits Earth once every few thousand years. Now they've downgraded the size of the Tunguska asteroid to just 100 foot across. These hit on average every few hundred years, and the last one we know of was in 1908.
The most likely scenario for a big destructive impact event is from a Tunguska-sized object.
It's a game of chance. Another Tunguska-sized asteroid might not strike for another 100 years, or it might strike tomorrow. Luckily, the Tunguska asteroid hit in an unpopulated area. In today's world, we might not be so fortunate. The question is, what can we do to protect ourselves from asteroids, big or small? In 1998, the US Congress instructs NASA to take action. It sets up the Space Guard Survey to identify and track any near-Earth asteroids that pose a threat to our planet. The first step is to identify the asteroids at least 3,000 feet across, the ones big enough to cause massive destruction if they ever hit Earth. So far, 1,100 asteroids this size have been located. The Catalina Stewart Observatory at the University of Arizona is part of this SpaceGuard network. Asteroid hunter Ed Bayshore and his team comb the skies for these giant asteroids.
Essentially what we need to do is we need to image an area on the sky 4 times over the course of about 40 minutes.
The computer takes 4 telescope images of the same patch of night sky. The stars stay still. But near Earth objects, the asteroids, move through frame.
So for instance, here's the first image of a field that we just observed. There's the second image, there's the third, and there's the fourth. When we start it blinking, we can see that we have an object right here in the field. As it turns out, that is probably an NEO by the way it's moving.
But what about the smaller asteroids? The ones we think wiped out the Clovis culture or exploded over Tunguska. Right now, Bayshore doesn't search for them at all.
There's many more objects that are smaller. And just because they're smaller doesn't make them not dangerous. In fact, we think the objects around 300 feet in diameter and larger, which are much more numerous, may actually represent a considerable threat.
Now space scientists are determined to track these smaller asteroids. Among them is a man who is no stranger to the hazards of outer space, former Apollo test pilot Rusty Schweikert.
Now, it's very important that we start looking for these smaller ones because they hit with much higher frequency. From 100 to 150 feet in diameter and larger, we can start having serious effects on the ground. They are huge in terms of natural disasters.
The smaller the asteroid, the harder they are to find. They move at around 50,000 miles per hour in orbits that are extremely hard to track.
Because we've only been looking for the biggest ones up until this time, our telescopes really aren't adequate to give us the information, the early warning that we need on the smaller objects.
Tracking small asteroids requires specialized telescopes. These are still years away from completion. But occasionally, astronomers get lucky. In 2004, they pick up a moving object in the sky. Closer inspection reveals it's an asteroid, and it's 900 foot across. Researchers name it Apophis, after the Egyptian god of evil and destruction. It is big enough to destroy an area almost the size of Texas, and it is coming our way. In 2004, at the Kitt Peak Observatory, Arizona, scientists spot a new and relatively small asteroid. It looks like it is on a collision course with Earth. It is called Apophis, and it's 900 feet across. Around 10 times the size of the asteroid that created Meteor Crater in Arizona. At the Massachusetts Institute of Technology, Dr. Richard Binzel tracks its trajectory.
An impact the size of Apophis in terms of the immediate damage would be regional, roughly the size of France in terms of its immediate catastrophic effects.
Based on initial observations, researchers believe it has a relatively high chance of hitting Earth in 2029. The asteroid poses a real threat. Binzel needs to discover what Apophis is made of. He studies the asteroid via a remote link to a telescope in the Mauna Kea Observatory, Hawaii.
The instrument we're using is a spectrometer. The different minerals that are present in asteroids have very critical absorption bands, or very fingerprints, if you will, in these wavelengths of light that let us distinguish between different kinds of compositions, different kinds of minerals.
No two asteroids are the same. Most are solid, but some are loose piles of rubble. The majority are made of rock, but some are composed of metals and other materials. Apophis turns out to be mostly made of chondrite, a type of rock.
We think that Apophis is like this type of meteorite. It's an LL chondrite meteorite, And the beauty is that we can measure the properties of this meteorite in the laboratory. And if we scale this meteorite up to the size of Apophis, which we think is about 900 feet across, the mass of Apophis is about 20 million tons. The energy that it would have if it hit the Earth is about 375 megatons, the kind of energy we usually talk about with nuclear arsenals. And that's more than 20,000 times the energy of the blast at Hiroshima.
With the asteroid's speed and orbit mapped, researchers can predict its trajectory more accurately. New data suggests that the 900-foot asteroid is headed this way in 2029. It will miss Earth by just 18,000 miles. A near miss in astronomical terms. But if Apophis had been on a collision course, what could we have done? The most obvious solution is a nuclear bomb. The theory is that a blast could shatter it into pieces. But this approach is risky. The blast fragments could continue on a collision course with Earth. And to make matters worse, they are now radioactive. Instead of eliminating the risk, a nuclear explosion could increase it. Earth could get hit by a cosmic shotgun blast, resulting in even more widespread devastation. One scientist alarmed by this scenario is Dr. Massimiliano Vasile of the University of Glasgow in Scotland.
What could happen is that the shock wave due to the explosion of the outer crust fragment the asteroid. So it might be that basically we have not just one asteroid on the collision course with the Earth, but we have 2 or 3 asteroids.
Scientists are racing to find a better solution. They have suggested attaching rocket engines to push the asteroid off course, or even solar sails to pull it into a different orbit. These are possibilities, but they sound like the stuff of science fiction. Researchers are putting their weight behind a more feasible solution: knock the asteroid off its collision course. The project's code name, Don Quixote. At the heart of the team is space mission analyst Chris Saunders from Kinetic Labs, England.
We are simply going to try and hit the asteroid and deflect it out of the way.
The theory is that a powerful strike delivered by a probe could knock the asteroid off its course, like a game of cosmic pool. Don Quixote is a 2-stage spacecraft made up of the impactor and the orbiter. The ion engine powers the orbiter to its target. Solar panels create an electric field which ionizes an ultralight fuel load of xenon gas, ejecting ions from the engine to thrust the craft towards the asteroid at up to 200,000 miles per hour. The aim is to catch the asteroid as far away from Earth as possible, so that even a tiny push will move it off course. The observer locks into orbit around the asteroid and guides the impactor to an inch-accurate surgical strike.
It would move the asteroid's orbit by maybe 50 to 100 meters. That would be enough for the asteroid to safely drift past the Earth.
If astronomers locate an incoming asteroid early enough, Don Quixote might be able to deflect it. But it's untested technology with a huge margin of error. Most scientists agree a backup plan is essential. To defend Earth from an asteroid strike, scientists have an ingenious and radical approach. Use an intense ray of light to vaporize part of the asteroid's surface, creating a jet of gas that will move it off course. It's a good theory, but right now the only place Massimiliano Vasile can test it is in the lab. He uses the Industrial Laser Lab at Glasgow University to gauge how much light energy it takes to move an asteroid.
We can see the effect of the light of the laser that basically was burning the rock. This is what we expect would happen in space when we focus the light of the sun on the surface of the asteroid. The effect that I obtain is exactly as if I had a rocket engine attached to the asteroid, but the difference is that the engine is the asteroid itself. This is in fact one of the most effective ways of deflecting the asteroid.
But shifting a full-scale asteroid would take a lot more light than an industrial laser. Luckily in space, we have a huge power source available, the sun. Vasile proposes using mirrors to focus sunlight on the asteroid, enough to vaporize its surface, just like the laser. But moving a 1,000-foot asteroid requires a mirror so large that no rocket is big enough to carry it into space. The solution? Use several small ones at once.
We propose to have a swarm of satellites, each one carrying a smaller mirror.
The mirrors would be around 60 feet across and precisely shaped to concentrate the solar energy, creating that vital jet of vaporized rock. Whatever system scientists end up using, the key is to catch the asteroid as early as possible. Astronaut Rusty Schweikert thinks it's vital to be prepared.
Even you and I driving our car, you and I typically have one chance in 10,000 that we're going to have an accident tomorrow if we're driving tomorrow. And because of that, we buy insurance. We're driving around the solar system on our planet totally uninsured. Why?
Someday, humanity will likely face another asteroid, like the one that exploded over Tunguska, or wiped out the Clovis culture. An asteroid just 150 feet across could kill tens of thousands of people, and we still don't know enough about them. The dangers and our lack of knowledge became all too apparent in September 2007. Carancas, Peru. Local people noticed strange lights in the sky, followed by a huge explosion. Villagers stumble on a 50-foot wide crater in the highlands. Locals claim it is caused by an asteroid, but not all scientists are convinced. Impact specialist Peter Schultz thinks it's a hoax.
My immediate reaction was, are you kidding me? This has really happened? It can't really be something that actually got through the atmosphere. This is science fiction. And the first pictures that came out, it looked like a B movie with this crater where Superman was going to walk out.
Schultz is disturbed by the size of the crater. It's tiny. An asteroid that small should never have made it through the Earth's atmosphere. It should have burnt up on entry. September 2007, a fireball blazes through the skies of the Peruvian highlands. It crashes to Earth near the village of Carancas in southern Peru, leaving a crater 50 feet in diameter. Eyewitnesses are mystified. At first, they think they're under attack.
We looked up at the sky and saw a smoky trail. First we thought it was a military plane. Then we saw that the object was approaching the ground, heading south. The workers said to me, I think that plane is out of control.
una estela, ¿no? Cuando pasan por el cielo.
We were really scared. Even animals are running away due to the loud noise.
One explanation is an asteroid strike. But how did an asteroid so small survive entry into the atmosphere? It should have disintegrated before impact. Peter Schultz, one of the world's leading impact specialists, travels to the site to investigate.
I heard the stories in the media, I saw the pictures, and I thought, oh my gosh, I've got to go there.
The impact has blasted chunks of Earth into the air, damaging a building 150 feet away.
Wow. Oh, jeez. Oh. Oh, my gosh. Wow.
Whatever caused this crater was powerful enough to blast 100 tons of soil across the landscape.
This is clearly the pre-existing soil. Everything was just simply turned upside down over this.
This has all the hallmarks of an asteroid crater, but Schultz is skeptical. He needs to find a fragment to prove it. He exploits a common characteristic of this kind of asteroid, its magnetism. The metallic fragment and the shape of the crater convinced Schultz that this was an asteroid strike. But how big was this asteroid? Eyewitnesses tell Schultz the angle of impact. Now if he can discover the speed, he should be able to discover the size. At the NASA Ames Research Center, Schultz examines the fragment of asteroid under a powerful microscope. It reveals the true story behind the impact.
The fragments were deformed. There were fractures, and they were in a pattern that happens at around 3 to 4 miles per second, almost 5 times a speeding bullet.
Schultz now has all the clues he needs to figure out the size of the asteroid.
From those pieces of information, the angle and the speed, we can determine how big it was. And it's probably somewhere between 3 feet and 6 feet.
It's an extraordinary discovery. Up until this moment, scientists believed rocky asteroids this small burned up before they hit the ground.
Here we have a puny thing, only about 3 to 6 feet across, that somehow made it to the surface. This shouldn't have happened. This just shouldn't have gotten through the atmosphere. In this case, it made it through. It not only made it through, but it hit hard.
How it got through exactly is still a mystery, but the fact that it did is alarming. If a tiny asteroid like the one that hit Caracas strikes a crowded city, it could potentially kill dozens, if not hundreds of people.
Will it kill people? Yeah. The clock is ticking. It's coming.
This is not one of those giant things. This is the type of thing that if it happened in New York, it would have caused some serious damage. It probably would have gone right through the ceiling of a tall building and gone through about 4 or 5 floors before it rested.
In Peru, we were thrown a hypervelocity curveball.
Rusty Schweikert believes that now is the time to take the threat from smaller asteroids seriously.
A hurricane, we can't prevent. A flood, we can maybe do some things to prevent. We can certainly mitigate against these things. But preventing is an unusual opportunity in a natural disaster. We can prevent this from happening. If we do our work with near-Earth objects, we can prevent asteroid impacts from ever happening.
There is little doubt that an asteroid will someday threaten the Earth. The question is, will we be prepared to deal with it in the not-too-distant future?